So we've been talking about acceleration, and in the last segment we got to the fact that deceleration is just as much an acceleration as acceleration is. It just happens in a special condition where the direction that an object is moving, remember velocity is a vector quantity, so direction is important, is going to be opposite the direction that the acceleration is applied in. You can have an acceleration applied in that direction, and if the object is moving in this direction, it's going to slow down, or it's going to move less and less and less fast, and eventually turn around, as long as these two are opposite right here. So let's do some examples and see what would happen if we have accelerations in one direction and velocities in another. Okay? So we have 8 scenarios right here. Okay, so the question is what's going to happen in each of these scenarios. So what this is saying right here is the initial velocity, that's what VI means. Initial velocity is 0, which means it is at rest, right? Rest, not moving. Okay, and let's say that an acceleration is applied to it. But the magnitude of that acceleration is 0. So there is no initial velocity and that there is no acceleration applied to it, or that the acceleration applied to it is 0. Is the velocity going to change? Well, no, because we know that an acceleration is a change in velocity. So if there's no acceleration, there's no change in velocity, so therefore there'll be no effect on the speed. So therefore, it's going to just sit there. Remains at rest. Right? Because there's no acceleration to change the fact that it's currently at rest. Okay. What if, however, that we have something at rest, okay, but an acceleration greater than 0, you might say a positive acceleration is applied to it. What's going to happen? It will accelerate or move faster. I'm going to say, I don't want to use accelerate too much because we're talking about that right now. It will increase velocity. We'll see this. Increase velocity in the positive direction. Okay? So it will be getting faster and faster and faster. The important thing here is in the positive direction. Okay? Well, what about this one right here? It's at rest, and we have an acceleration less than 0, right, or negative. Well, it's going to increase its velocity, all right, but it's going to be moving in the negative direction. In the negative direction, I should make it more clear right there. Right, in the negative direction, it's going to be moving faster and faster and faster in the negative direction. You can't move slower than 0, but you can move faster and faster in the negative or the whatever direction you consider to be negative. Because remember, velocity and acceleration are both vector quantities. Direction is going to be important. You can have a positive or a negative value right there. Okay, what if the initial velocity is greater than 0? What does that mean? Well, it's moving. It's moving in the positive direction right here. Okay, great. But what if the acceleration is 0? The acceleration applied to it. Well, that means it continues to move, or continues moving, and this is important, at a constant speed. Speed in the positive direction. All right, so it does not change its speed. It maintains this initial velocity right here. All right. So we have an initial velocity greater than 0 here, but we also have a greater than 0 acceleration. All right. What's going to happen here? Well, it means it's going to move, or it's going to increase its velocity in the positive direction. All right, very much like this one right here. Okay, right? Because there's a positive acceleration applied to it. But what's the difference? Well, this starts with a velocity. This one starts with a velocity of 0. I should say this starts with a non-zero velocity. This is 0. So this thing's already moving as it goes faster and faster and faster. This has to start from rest. So think of it as being like this one is a car that starts moving from a stoplight, And this one right here is a car that maybe a NASCAR race that they're doing a running start and they pass the start line and then they mash on the gas and then they accelerate faster and faster. So they're already moving, but they still increase the velocity in the positive direction. All right, let's see if we can move through the last few of these a little bit quicker. So we have an initial velocity greater than 0, so it's positive. But this is kind of interesting. We have an acceleration that's negative. So this means it will decrease velocity in the positive direction. All right, or you might say it will slow down in the positive direction and then maybe even stop and move in the negative direction. Does that make sense? All right, if given enough time, this thing moving in the positive direction will be moving forward, but with this negative acceleration, it will slow down and then eventually start accelerating in the negative direction. I should say accelerate in the negative direction right there. Okay? Initial velocity is less than 0, so initial velocity is negative. No acceleration. What happens here? It continues moving. Continues moving at constant speed, right? Constant speed in negative the direction. All right? Whatever the direction that's negative, it keeps it moving at a constant rate, a constant velocity in that direction. All right? Less than 0 velocity, positive acceleration. So we have a decrease velocity in negative direction, maybe even stops, and moves in the positive direction. All right, so we have a positive acceleration, but since we had a negative velocity, this positive acceleration works as a deceleration to this. So this object was called to the left negative. This thing was moving negatively, but there's a positive acceleration. It's going to become less negative and then more positive. So while that's slowing down, we say it's decelerating in the negative direction. All right, and lastly, we have a negative velocity and a negative acceleration. This just means it increases the velocity in the negative direction. All right, very much like this one right up here. But again, this is starting from rest. This is starting from a moving start in the negative direction. So it's like NASCAR cars that are all driving the wrong way on the track, maybe. Something like that. Okay? All right. So now let's see if we can apply this to some graphs. All right, we've got 4 graphs right here. We've got A, B, C, and D. It would be nice if they were different colors, but that's all right. I'm going to make A. I'm going to make that red. Okay, I'm going to make B. I'm going to make it blue. C, I'm going to make green. And D, I'm going to make, I don't know, orange. Okay, and so let's ask ourselves, is the object accelerating or decelerating? All right, well, what is going on right here? Let's look at just A for a second, all right? A, it is starting out with a positive acceleration. I'm sorry, with a positive velocity, right? This is above 0 right there, okay? Starting with a positive velocity, and we have a positive slope. Up here, we've got a positive change in velocity over time, all right? So if we've got that change in velocity over change in time, that means it's a positive acceleration. So what's going to happen? It's going to accelerate. It's going to accelerate in the positive direction. Okay? And just move faster and faster and faster. All right, but how about part B, though? We've got a little bit of a difference right here. We're still starting with a positive velocity. But look, we now have a negative slope. We've got a negative change in velocity over time. So what do we say happens if we have a positive velocity, but we have a negative acceleration? There's a negative change in velocity over time. Well, that means it's going to decelerate. It's going to decelerate in the positive direction, and it may even come to a stop. Look, if we give it enough time, it's going to get slower and slower and slower, and if this line crosses the 0 line right here, If that green line were to extend down, what is the velocity? That's a velocity of 0. So the thing is getting slower and slower and slower, and eventually it'll stop. It may even go backwards, but we don't know quite just yet. All right, how about C? Well, it starts out right here with a negative velocity, right? It's below 0. But we have a positive slope right there. Okay? So originally it was going in the negative direction, but it's got a positive change in velocity over change in time. That means it's got a positive acceleration, right? Positive acceleration. So if the acceleration and the velocity are different signs, that means it's going to decelerate. But it's going to decelerate in the negative direction. It wasn't moving negatively, but now it's moving slower negatively and slower and slower and slower, and eventually it may even just stop and go positive, but we don't know. All right, and lastly, D right here. It's got an initial velocity that is negative, and it has a negative slope. There's a negative change in velocity over change in time. So it's that velocity, I oftentimes say kind of jokingly that it's the velocity gets negativer and negativer. All right, it's got a negative acceleration. All right, so it gets faster and faster in the negative direction. So we can say it's going to decelerate, or sorry, it's going to be to accelerate. ACCELERATE. It's going to accelerate in the negative direction. All right, so whatever direction that is, it's going to go faster and faster in the negative direction. All right, one or two last quick slides about reading graphs and interpreting them, and then we'll be done with this section right here. So, on a position versus time graph, all right. So here's a position versus time. All right, x over t. Here is our velocity versus time, and here's our acceleration versus time, like that right there. That last one wasn't very good. Acceleration versus time. All right, and I oftentimes color code them too. Velocity I usually make, or position over time I make green. So in a position versus time, the slope is going to equal the velocity. At any one point right here, you've got one slope, and then here's another slope right here. All these tangent lines are the slope at that one point, but that means the velocity at that point. All right, if we were to do kind of an average velocity and take the slope of that secant line, or the slope of the secant line would be the average velocity. But at any one point, the slope of the graph here, here, or here equals the velocity. All right, I usually do the velocity versus time graphs in red. All right. So on a velocity versus time graph, the slope equals the acceleration. All right, so here is the slope right here. It's the acceleration, because after all, acceleration is change in velocity, or change in rise over change in time. Hopefully that's big enough for you that you can see. All right, but even more importantly than that, let me draw another position versus time, or sorry, velocity versus time graph. Let me redraw that down here. Here's our velocity, here's our time, and then here is our red acceleration line. So the slope is the acceleration, okay? But say between, let's see, time 0 and that time right there, all right? The area under the curve from here to here, all right? The area under the curve equals the distance traveled. Area under curve. Now, there really is no curve right here. It's a straight line, and that's actually pretty easy for us to calculate. But what would be the area of this right here? Well, that would be 1/2 base times the height, right? If that's defining the area of a triangle. Well, why is that? Well, since we know that velocity equals change in distance over change in time, what are we doing right here to get this area? We're taking this times that, right? Actually, 1/2 this times that, but it's velocity times time. What did we do to get velocity times time? That means we moved that up right there. We took time and multiplied it up, which really means the velocity times time equals that displacement or distance traveled. So this in here, that shaded area under a velocity versus time graph is going to be equal to the distance traveled. The slope equals the acceleration. The shaded part under the graph for the time increment that we care about is going to equal that distance. All right? Now, similarly, we can look at acceleration versus time graphs. Let's say we've got a constant acceleration, so a constant positive acceleration right there. All right, and for a certain period of time t, from 0 to right there, we have a certain chunk of time that it accelerates at that point in time right there. What does the area under the curve mean here? All right, again, it's not really a curve, but you might see the area under the graph for that period of time. That right in there, what would that equal? Okay, well, what do you do to get that area? You take the acceleration times the time, right? To find that area, this is the vertical is acceleration, the horizontal is time. What is acceleration times time? Acceleration times time equals velocity, because we know that acceleration equals change in velocity over time. All right? I should really say change in velocity right there. All right? We know this is true. The change in velocity over time, if we have a velocity versus time graph, the acceleration is that slope right there. So if we have acceleration times time, that means we multiply that time up, and so this shaded area equals the change in velocity. All right? Change in velocity. So we can read graphs, we can read the slope of graphs, but we can also read the shaded part underneath graphs to get information about what is happening as well. Let's look at this last little graph right here, and then we'll be done. All right, what has happened right here? Well, we have a velocity versus time graph. All right, and it was started at a certain velocity of 1.50 meters per second. All right. So what is the shaded area underneath velocity versus time? Well, this is going to be the change in displacement, right? Change in displacement. Can you see that? Oh, probably not. I wrote green on light blue. That's terrible. Let's write it in red. This whole shaded area right here is going to be the change in displacement, because velocity times time equals that change in displacement, or the distance that you traveled. So how do we get that area? Well, we take this box right here. You can find this box, right? It's 1.5 meters per second times 5 seconds. All right, 1.5 meters per second times 5. So that's that right there. And so that would be what is 1.5 times 5? That's 7.5, right? Meters. And this top part right here, we take 1/2 the base, so 1/2 times 5 times the height. What is the height difference between here and here? Well, 1.5 to 13.5. That's 12, right? 12 meters per second difference. So that would be 30 meters. And so for this whole thing, the whole displacement is actually going to be 37.5 meters, because you have to take this shaded area under the graph and this shaded area under the graph right there. All right? So that tells us that our total displacement, TOT for total, equals 37.5 meters. And we found that all by reading this shaded area under the graph. All right? I hope that helps. Sorry this segment took a little bit longer than usual, but acceleration is some pretty heady stuff, and we're going to be looking at it a lot. If you have any questions, make sure you come see me or ask me, shoot me a question on Schoology. And in the meantime, thanks for watching, and I'll see you on the next one.